Any sufficiently advanced technology is indistinguishable from magic. Welcome to the Throttle and Roast podcast. I'm your host, Niels Meersschaert. In the roughly 125 years that the motorcycle has existed, technology has continued to advance how the bikes perform as well as add in creature comforts. We'll look at some of the innovations that have occurred in the past and how they're becoming more commonplace today. We'll also try to see where the future is headed, what could be some of the next evolutions of technology applied to motorcycles. So let's start with a bit of the history thus far. The very first motorcycles appeared in the late 1800s, with major mass production beginning around the turn of the century. So we're really only about 125 years into the evolution of the motorcycle. Now, we did cover in more detail a little bit of this cultural journey of motorcycles through history in an earlier episode, and I'll link to that episode in the show notes. But I want to kind of recap a couple of the highlights of what has occurred for motorcycles over the past roughly more than a century. So the very first early bikes tended to have a trailing link style front suspension. This was just a byproduct of looking at how they had produced, for example, horse-drawn wagons in the past. They applied that same view to have a bit of suspension. Remember, some of the very first motorcycles even had a hard tail. So the only suspension on the bike was in this front suspension. I started to see a little bit of the evolution in this front suspension design in the 1920s as telescopic forks were coming onto the scene. And ironically, of course, BMW was the innovator who brought this to the market at that time. So the very first motorcycles were beginning to evolve. And this form of front suspension, the telescopic fork, is the most prevalent today. And that really got its start about a century ago. Now, into the 1940s, we started to see some hydraulic dampening in those forks, along with some better brakes and lights. This was beginning to continue to evolve, making the motorcycle a little bit more comfortable. The very first few lights that were on bikes were kind of more suggestions of light. You really couldn't see much more than maybe 10 or 20 feet in front of you with those early lights. So they really didn't project a lot. And therefore you had to keep your road speed a little bit lower. And if we think of the 1960s into the 70s, this was the beginning of that peak era of motorcycles, at least from a volume perspective. This is why when you look at a lot of classic bikes that are still ridden today, many of them will be from that era of the 1960s and 70s because there was just such a high volume of motorcycles produced. We also started to see a little bit of evolution in the engine really beginning in the 1980s. This is when you started to see water cooling beginning to appear. The tolerances in the engine could be made much tighter because you didn't have to allow for so much expansion of the components as it got into the heat cycle. And therefore, we were able to have a higher power output. In the 1990s, we saw fuel injection starting to replace carburetors. And this allowed us to no longer have issues at altitude with having to constantly retune the carburetors. It made it for a much simpler experience for a lot of motorcyclists. The basic disc brakes started to appear in the 1970s. It really was an era of much more on the mechanical end of the equation. And in the past 25 years, this is where we've started to see a very rapid acceleration of technology that's been appearing on bikes. And a lot of it has been more on the supporting electronic nature rather than on the mechanical. ABS and traction control became available in the early 2000s. Of course, what this is providing the ability to have some electronics that were recognizing differentials in rotation rates between the front and the rear wheel, and therefore making adjustments to either your braking performance. So if you started to see, let's say the front brake was slowing down more than the rear wheel was, it would then start to pulse that front brake to try to maintain traction. Traction control kind of works in the same way, just inverted. It's using the same sort of sensors, but now what it's doing is it's holding back the throttle to allow you to keep from overwhelming that rear tire. Another advance that we got that was sort of factored into this was sort of ride-by-wire. This also began to appear in some of the early 2000s was not widespread, but certainly was beginning to appear. And what this was is the old way that we had for acceleration was managed by your throttle grip, which would just rotate, would actually have a connection of a cable in there. And that cable would basically be rotating as the throttle grip was. And therefore, it would pull it within the throttle cable sleeve, connecting all the way down to your throttle bodies. And that would actually physically move the throttle bodies based upon the rotation and effectively the cam that was set up into the throttle grip. So you didn't have as much control over how the rate of change of throttle was occurring based upon the rotation in the throttle grip versus what was happening at the throttle bodies. But with ride-by-wire, all of a sudden we've decoupled these. Essentially, the throttle grip is just sending a signal to a computer of how much throttle is being requested. And then the computer is going to actuate a movement into the throttle body. You have effectively the computer in the middle that is interpreting your request for power and adjusting that on the throttle bodies directly. Now, much of this tech, of course, was coming from sport bikes, where advances to keep on top of the podium kept manufacturers pushing the envelope. Over time, these advancements, these improvements in the capabilities of the bikes, slowly started to trickle down into more of your everyday mainstream bikes. Today, it's really hard to find a bike on the market today that still has carburetors. The old KLR 650 would be a great example. The DRZ 400 was another example that just in the past few years have switched from being carbureted to being fully fuel injected. So those last vestiges that were still holding out for all these decades at this point now all have fuel injection. The other thing I would say is look at ABS. It's really difficult to find a motorcycle today that doesn't have ABS on it. In fact, I think the cheapest motorcycle in the United States is the Honda Navi. It's about $2,000 and it has front ABS. It doesn't have rear ABS, but it does have front ABS. So a lot of this stuff has been democratized and made more broadly available. Computers began to hit the internet era as we got into the late 90s, into the 2000s, and software really became the king. And our bikes have started to take this on as well, with many of them offering onboard computers. Some of these computers were very simple. They were taking that information from the throttle body and the throttle grip and adjusting the performance of the bike accordingly. Others just were simplistic electronic odometers and service indicators from those onboard odometers. But this engine management is really where a lot of the innovation started to take place. And of course, it started in the sport bikes, but these throttle curves could be tuned in software. And therefore, the era of ride modes began to arrive in the 2010s. You could now have a kind of a normal ride mode. You could have a sport ride mode. You could have a rain ride mode. How twitchy, if you will, the throttle grip and how much it would affect onto the rear tire could actually be adjusted. You could have effectively multiple different bike feeling just by changing the ride mode on the bike. This is really cool because now when you have a very high performance bike like a sport bike and you're riding it in the rain, you don't want to have that instant throttle response. You want it to be a little bit slowed down. Well, this was now possible to do. Another feature that we got in the 2010s was cornering ABS. So if you think of a traditional ABS system, it works really great when you're stopping in a straight line in your vertical. Well, if you're trying to hit the brakes in a corner, you've got to realize that part of the grip of the tire is being used to turn the bike. So the amount that's available is reduced. So cornering ABS would recognize that the bike was leaned over and adjust how much it was applying onto the brakes in that situation to maximize traction, both for turning and for stopping. Another technology that we started to see appearing on a lot of motorcycles, especially the sport bikes to begin with, were quick shifters. This allowed you, in the beginning, it was a clutchless upshift. What this did is it would, when you sent the signal to do an upshift, there was actually a little body that would recognize your movement of that, but it wouldn't physically move the internals for shifting the gear. And then it would send a signal to the bike computer for that ride-by-wire to actually hold off on the throttle for a moment to adjust it so that the RPM was at where the next RPM would be in the rev range for that next gear. And then once it got there, it would then allow the bike to upshift into the next gear. The thing is, what I just described, it took a lot longer for me to describe it than how long it actually takes in the bike. So from a rider's perspective, the change in gear appeared instantaneous. Meanwhile, the computer was doing all those calculations in a very quick manner. Now, we started to also see some smartphone connectivity. This began pretty much in the mid to late 2010s. I covered a little bit of this in the BMW Motorrad app episode. I'll put the link in the show notes for that. We've also begun to see some improvements in materials, allowing some insane levels of power output, even on street level bikes. So think of the Ducati Panigale V4R. This has in its street bike configuration 208 horsepower out of a 998cc engine. If you're using it for track use, that power jumps up to 239 horsepower. This is all out of basically a 1-liter engine. So the power to capacity ratio is really, really remarkable of just how much power is coming out of it. And in most cases, these are still naturally aspirated. The remarkable amount of power that we're getting just from the improvement in materials, because if you look at how materials have advanced, the strength of the engine components, if we didn't have that in place, we wouldn't be able to have that kind of a power ratio in such a small amount of space. The other thing that technology has allowed us to do from a materials perspective is allow our tires to have even more grip while still having a good amount of longevity, at least compared to the past. So now you're going to have sport bike tires that are having an insane amount of grip, but still allowing you to have the same amount of longevity that we had in the past. And usually there's a trade-off between grip and longevity because you're going to make the tire a little bit softer and therefore it won't last as long. Well, we're able to get more and more grip out of a tire while still maintaining that same amount of longevity. Or in other applications, let's say in a cruiser tire, where we don't need as much grip as we would have in other applications, we can have still even extended longevity of how many miles you're able to get on a tire. Now, I mentioned how quick shifters began to appear pretty much in that early 2010s, and predominantly on sport bikes, originally starting with just an upshift. They started to then incorporate downshifting as well, and it would work in the same manner. But what would happen is that when you asked for that downshift, it would actually blip the throttle a little bit to get the revs to match. And this is really cool technology that allowed us to have much faster upshifts as well as downshifts. And this technology has started to trickle out into other segments of motorcycling, not just on the sport bikes. So as an example, on my 2015 BMW S1000R, I did have the upshift quick shifter, but the downshifts I still had to do manually on that particular bike. But that's now a 10-year-old motorcycle. But my 2025 BMW F900 GS, which is an adventure bike, actually has quick shift both up and down. It's not a sport bike, it's an adventure bike. The capability to have quick shifting is getting far more widespread than it was even just a decade ago. So we've gotten more features. We've gotten advanced traction control and ABS. We've gotten better at engine management. And this has really been, I'd say, the driving force. And a lot of it's coming from what we're seeing in some other industries. So the computer industry, the software industry has been really moving at such a fast pace with the internet. We're now seeing that applied into mechanical situations with engine management and some of the other supporting materials such as that traction control and ABS. But we've also applied this into some alternative propulsion forms, such as electric motorcycles. Now, electric motorcycles, as we've talked about in some earlier episodes, one of the big benefits of them is that they have effectively a flat torque curve. Now, another thing you get, we talked about in our comfort episode, is the engine vibration can actually be a little bit fatiguing on a motorcycle. Well, an electric motorcycle, of course, has no engine vibration because it's just a motor. There's no reciprocating mass that you would get in a typical piston-driven engine. you just get this rotation, almost like a turbine engine. And so there's really no vibration that exists. There's no loud exhaust that's going to annoy your neighbors. But I'd say the trade off for this, and this is where I think why electric motorcycles have not taken off, at least here in the United States, is many of them just have no character. And this is an aspect that many motorcyclists love about their motorcycles is that vibration, especially if you look at the American cruiser market. They love that potato sound from a Harley V-twin, and that vibration that you get, that's part of the experience and part of what they love. So electric motorcycles haven't had that quite yet. If we think of modern bikes also, one of the other aspects that has come in from some of this movement of technology from other areas is the IMU stability systems. If you think of the sensors that are in your smartphone that allows it to recognize its position in 3D space from the accelerometers, are you rotating it to the left, to the right, up or down? That same technology is now applied and the sensors are applied in a motorcycle situation to allow it to recognize the position of the bike in 3D space and then adjust the stability systems accordingly. Now, today, most of these stability systems work by retarding the throttle. The idea being is if you have too much throttle application, the bike chassis can get upset, and this way it can retard that throttle to keep the bike a little bit more stable than it would have been otherwise. Another bit that we're starting to see is some of the stuff that was in cars is starting to filter down into motorcycles. And we could think of ABS was perhaps that first one, because ABS arrived in cars in the 80s and 90s, and then it came into motorcycles in the 2000s. But we're starting to see some other things like adaptive cruise control. This allows your bike to maintain a following distance from the vehicle in front of it with a radar sensor that is recognizing the distance to the vehicle in front of it, and it'll adjust the throttle and even hit the brakes to maintain that following distance. Blind spot indicators are appearing in the mirrors to allow the rider to know that there is an obstacle on either side of them, so they don't immediately just turn into that other lane and run into that other vehicle. And another one that we are starting to see, not as broadly yet, is the automatic shifting. You'll see this on some of the Honda motorcycles, some of the BMWs now in the past year with the 1300 series, for example. KTM has them. These bikes no longer even have a physical clutch lever on the left handlebar anymore. And these are often called a dual clutch transmission. So just like in sports cars, they offer the rider the ability to still select the gear with their foot, or even allow the bike to just fully automate and shift through the gears on its own. But this has an opportunity to make riding maybe a little bit more open to new riders where they're not even buying manual transmissions in cars anymore. So many of the people who are maybe coming of age and getting their licenses today have never driven a manual transmission car. So to ask them to A, learn how to ride a motorcycle, and B, learn how to also operate a manual transmission might be a challenge for them. So having some of these other capabilities can extend the market for making it more perhaps approachable for some of these new riders. So that kind of brings us to where we are from a motorcycle technology perspective today. And prognostication is always difficult, but I'm going to try to kind of tease out a little bit of where I see some likelihood of where we're going to start to see some of these technologies continue to emerge in the future for motorcycles. I'd say electronics is really where I still see the greatest opportunity for advancement because it has applications that are applying in other fields that we can sort of borrow into the technology used in motorcycles. As an example, as I covered in that BMW Motorrad app, there more and more bikes are coming with connectivity with your phone than ever before. And some motorcycles, like some models from Honda and Indian, even have CarPlay integration. So you can actually see your full CarPlay interface directly on the bike's TFT. So entertainment, navigation, and more are at your fingertips on a growing number of bikes. And as more bikes move over to TFTs, adding in these software features almost becomes a minimal additional expense. The displays are cheaper than ever before, so my expectation is that this will continue to become more and more prevalent, which may come as a negative to some of the classically styled purists out there. But I think bikes will follow cars in this regard and have more software and more screens. And at the same time, on a motorcycle, we really need to try to minimize the use of touchscreens and still have physical controls because you don't want to be removing your hand from the handlebar to interact and manipulate a on-screen display. This is where some of the technology has been used by some manufacturers. For example, BMW's Wonder Wheel, the multi-controller that they use to manage that TFT, is a great way to keep your hand on the handlebar, but still allow you to manipulate that TFT and the display that's on there. I'm expecting, though, that some of this stuff will start to become a little bit more standardized of what that interface is. Just like today, you can't find a motorcycle on the market that doesn't have the clutch on the left side, throttle grip on the right, the front brake on the right-hand side, the rear brake on the right foot, and the shift gear on the left foot. That's standardized across everything today. Even the switch gear for your turn signals is much more standardized than it was in the past. So I expect we'll start to have some of these physical controls for manipulating the TFT start to also become more standardized. The other one that I think we have to look at more seriously is, and we touched a little bit about this with electric motorcycles are starting to come onto the scene, but I really think we're going to start to see more of these, I'll call them more generally, alternative powertrains. Now, when most people talk about electric vehicles, they often really mean a BEV or a battery electric vehicle. And this is really a combination of the powertrain, which is the electric motor, and the energy source, which in this case would be a battery. But this isn't the only way for electric vehicles to be packaged. Battery electric vehicles have some limitations that make them less appealing for motorcycle use. For example, on a motorcycle, we have limited physical space. This means we have limited dimensions into which we can fit a battery. In a car or in a truck, for example, you have a lot more physical space into which you can have a larger battery, which can give you a range that is far beyond what you would typically drive in a given day. Whereas on a motorcycle, we're pretty much peaking out at roughly about 100 miles of range in real world riding use. Some of them will claim more than that. They might claim 150, 160 miles, but that's usually in a urban environment where you're in stop and go, which is a little bit better for electric motors. Now, another issue that we have, this applies to most vehicles that are battery electric vehicles in general, which is there's limited charging options outside of highways or urban environments. So if you're, let's say, parking at your office, there may be some charge situations where you can plug in and charge. That's great. But for a lot of motorcyclists, we're oftentimes riding into maybe more of the less populated areas where there's the fun roads. These might be mountainous areas. They might be some of the areas that have more twists and turns around lakes. That's where we like to ride the bikes. The thing is, there's not as many charging options available in those areas. Now, if you're along a major highway, sure, you can pull over and probably find a charging station. But when you're out in the boonies, so to speak, it's a little bit harder for it. The other thing that happens with this limited capacity, it reduces the charging rate. And this is where I think a lot of people don't understand some of the physical constraints that happen with batteries in general that are used for electric vehicles. Most of the batteries produced today are based on lithium. So they might be a lithium polymer, they might be a lithium ion. In general, when you start to think about these, the maximum charge rate expressed in amps is really based upon the overall capacity of the battery. So for example, if I had a 5,000 milliamp battery, I might say that I could safely charge that at 5 amps. And that's a pretty safe charge rate for most batteries. You can extend that in certain situations based upon how the battery has been constructed, or if you had, for example, liquid cooling that allowed it to keep its temperature from climbing too quickly as you're inducing a higher charge. But all that added complexity of water cooling surrounding the battery starts to make it really hard to package in a very tight space like we have on a motorcycle. So in a large vehicle application, such as in a car or a truck, I might be able to fully charge a battery in an hour. The thing is that for a lot of people, when they're pulling over to the side of the road, they're in the mountains, they're having a fun ride, they don't want to wait an hour to charge that battery up. They want to do just like they would do with filling up a gasoline tank. They want to do it in a handful of minutes at most. The real issue is that in a larger vehicle, I don't care about fully charging the battery necessarily. I care about charging the battery enough for me to get to my next stop. So if I could charge up in 5 or 10 minutes, to get, let's say, 100 miles of range, which is good enough before I want to take my next stop, that's fine. But in a motorcycle where the maximum capacity of the battery is maybe 100 miles, I've got to wait that whole hour to fully charge it. And this is what I think is hurting us from a application for batteries in a motorcycle. But there are some other ways in which you can do this. So one is a fuel cell could be an alternative that we could start to see applied into motorcycles. It's something that's not quite as popular today as the battery electric vehicles, but companies like Toyota and others have been building some vehicles that use fuel cells as the energy source for the electric motors. And this is where I really want to distinguish between the powertrain, meaning what's actually providing the motive force to the wheels, which would be an electric motor, versus the energy source. So battery electric vehicles, as I said, use an energy source of a battery, whereas a fuel cell is a way in which it is converting that fuel, and then from there, it is generating electricity to power the electric motor. So most of the fuel cells today are actually based on hydrogen, and this is produced as a liquid fuel pushed into a tank, and refilling the tank can take a few minutes, just like gasoline. If you added a hydrogen pump at all of the filling stations that existed already around the globe, this could be a far easier way for people to be able to refill, even though they are producing it with an electric vehicle. What's happening inside of these vehicles is the same sort of oxygenation that you would have with gasoline. But the cool thing is, because if you're combining hydrogen with oxygen, well, what do you get as your output? Well, it's H2O. That's just water. So their tailpipe emissions are just water. So you get the same emission benefits from a battery electric vehicle, but you get the advantage of much faster refilling of range. Now, while you're commuting, a battery electric vehicle can make a lot of sense because your vehicle is going to be parked either at your office or at home, and therefore the amount of time that it takes to charge is less of an issue. But for other types of trips, especially the leisure trips that we would do in a motorcycle, many of us would be better served with these fuel cells. Now, it doesn't have to be only an either or of only we do electric vehicle or we do a gasoline. You could also start to look at some hybrids. Pairing a gasoline engine with a battery offers another way in which we could extend range, reduce emissions, but still deal with the reality of charging infrastructure as it exists today. And I really want to look at these in sort of two avenues. One would be an engine powertrain with electric assist. There really, an electric motor is put between the engine and the drivetrain. And this allows for increased torque and can even fully drive the vehicle for short bursts only via electric power. And the battery on board is often significantly smaller than you'd find on a full battery electric vehicle. And in some cases, these are plug-in hybrids, so it'd be a little bit larger battery. And you could charge this at home or at work, and it might give you a range of, let's say, maybe 50 miles, which tends to be a typical person's daily commute on a vehicle. So you could be fully electric for your normal daily commutes. But because it has a normal gasoline engine, if you needed to go extended range, you can still do this now fully on a gasoline and not have any of the challenges of worrying about finding charging infrastructure along the way. This is possible to package into a motorcycle to allow us to have that capacity and really rely upon that smaller battery that we could use maybe for some of that commuting. We only need 20, 30, 50 miles of range rather than that full 100. But we still have the engine to allow us to have that extended range if we so need it. There are some challenges with it. It is a more complex system. You're going to have both effectively a electric as well as the gasoline engine. But if you are looking at it from a perspective of what it allows you to do and addressing some of the emission requirements that are happening around the globe, this does have a benefit for us as motorcyclists. The other issue that I'd say, and this is where for battery electric vehicles, specifically for motorcycles that I would be concerned with, is for a regular car, if you're using the battery frequently and you charged it up to, let's say, 100%, and then you use it the next day. But on a motorcycle, a lot of motorcyclists don't use their motorcycle every single day, which means it's going to be sitting at whatever last charge level it was at. And most lithium-based batteries really don't like to be left at full charge for an extended period of time. It actually can damage the battery and could cause premature failure. Having a smaller battery that you use in a hybrid situation for a motorcycle might make this a little bit more viable, that you're not leaving a battery charged, especially a high capacity battery, for an extended period of time. But there's another way that we could package a hybrid. Rather than having a gasoline engine with a electric motor assist, you could have a fully electric powertrain, just as you would have in a battery electric vehicle, and use the engine as a generator. So this becomes a different, almost mindset, if you will. Most of the time that you are powering the vehicle, it's using the battery that's on board and the electric vehicle motor to power the motorcycle. And you'd only fire up the engine when you need to recharge the battery if you didn't have enough range at that point. So it kind of works a little differently. You'd get all of the benefits of an electric motorcycle, of that instant torque, but still have the engine available to extend your range. Now, the next area that I think is where we're going to start to see some really improvements or applications into motorcycles is more advanced assistive systems than we have today. Today, we've got traction control, we have ABS, and we have some stability. And I think these will continue to advance. But one of the things that we've started to see, the chat GPTs, the various other players out there in the AI space, is there could be more of an emphasis on machine learning and AI brought into motorcycles. And I think this could be really interesting to see from a stability perspective. Today, when you look at stability control systems, what they do is they retard the throttle. And that's the only interface that they have for adjusting the stability of the motorcycle. Well, we might be able to see some other types of adjustments that the internal computer could do to help to stabilize the motorcycle in whatever situation it gets into. So it might be able to add in, for example, some braking. Maybe it's going to be able to choose whether it applies the front or the rear brake to stabilize the suspension of the bike and keep it loaded. This is where a more advanced rider would actually be able to do this and think of it. But you could make this available to a general rider. Maybe they got a little too hot into a corner, but now the stability control system can adjust that braking front and rear to keep the bike in a stable position. The other thing that we could do is even have the bike adjust steering input. So it could recognize where your position is and then adjust the bike. Maybe it takes some of that lean angle out. Maybe it adds a little bit more lean angle. And if it has sensors that are looking at what the road conditions are, how the curve of the road is, any obstacles that might have gotten in the way, it can take some of these evasive maneuvers or road following to be smart about it. So the AI could actually start to help augment what you would do as a normal rider. Now, there's going to be some people who will complain about this and say, I don't want the bike to be riding itself. I want to do it. But think of these as the systems that are there for more of a you're getting out of control situation, and having that additional intelligence could be really interesting. So to support this, I think we're going to see a few things. Number one is we're going to have some additional sensors. Some of today's cars have radar to help them see obstacles and provide automated braking. This works really well for that adaptive cruise control as an example. The newer bikes that have this adaptive cruise control will continue to do the same. But if I think of that now as an additional sensor, that input could be used not only for my adaptive cruise control, but I could start to use it for obstacle avoidance. And there's a couple of other ways that you can have this intelligence, that is that sensor input coming in. We might even start to see some network communication. Maybe more vehicles start to become a mesh of interconnection, basically sharing what their position is, what their intended direction of travel is, and communicating this to other vehicles as well as to nearby traffic lights. Now, how often as a motorcyclist have you been stuck at a light waiting for it to turn and no vehicles are coming the other way? Or if the light has the sensors that are under the roadway to recognize vehicles, but of course on a motorcycle it tends to be too light to actually be able to trigger it. There's not enough metal to communicate to the sensors that there is a vehicle waiting to turn. So you sit for minutes and minutes and minutes at this red light and there's no vehicles coming the other way. It's really frustrating. Well, if you had this sort of mesh communication of telling them in the traffic systems that there is actually a vehicle waiting there, that's not relying upon a physical sensor that's used under the roadway, but more radio signals, you could actually then communicate this. If you were having vehicles that were going to turn left in front of you, they would actually know that that's going to come in. And now I can start to do a little bit of mitigation in that situation. With AI software, we might even have these systems become even better. You could enable it to predict when those vehicles are going to be crossing your path. That's one of the major issues for motorcycle crashes is when a vehicle turns in front of you. So here in the US, we often refer to this as left turning vehicles because we're riding on the right-hand side of the road, while in the UK and other countries where they drive on the left, it would be the right turning vehicle that would be the predominant cause for these type of collisions. So if you have this interconnection between these vehicles, you could know that that vehicle was going to turn. You could know that the vehicle is not just indicating that it's going to turn, but that it actually starts to move forward, and therefore it could recognize and take any sort of evasive maneuver to avoid a collision. The intelligence that exists combined with the sensors on the bike could make this possible. Now, another one that I talked about with the BMW Motorrad app deep dive was I talked about the BMW smart glasses that give you some information in a heads-up display, which is really cool of what it could do. It can provide your current speed. It can provide what the speed limit is. It may even provide some navigation prompts. But if we have that additional sensor data, maybe even that interconnection of the network, I could start to have where the system is doing a little bit more. We have ability within a lot of AI systems today to do what's called computer vision. I can identify an object that's within the field of view of a camera and say what that object is. So you could have a system that is today recognizing that there's a vehicle that's turning behind a other vehicle, and it maybe caught a glimpse of it early, and it's tracking the predicted path of that vehicle, which is now going to come in front of you. By having that awareness of what is happening, of all the sensors surrounding you, or maybe there's a kid who runs out in front of the road, or a dog runs out in front of you, having that awareness of seeing those objects and their predicted path, it can give some suggestions to you within this heads-up display of some warning parts of what might be coming together. You could even have, let's say, if there's a sudden traffic stop up ahead, where maybe there was an accident. Well, this could be communicated and you could start to slow down in advance because you're aware that the traffic is not just in front of you, but it's completely stopped. Having that visibility in that heads-up display could be interesting to help mitigate some of the safety impacts. And this, of course, would apply not just into motorcycles, but into all vehicles. But in a motorcycle-specific context, because of our more exposed nature, I think this could be really interesting. The other one that I think that you'll start to see is related to safety gear. We're starting to see things like airbags become more prevalent. And there's really two sort of approaches for airbags today. There's the tethered approach, which is the one that was originally out there. There's a physical tether that you attach to your bike, and it's connected to a CO2 cartridge that when the tether is pulled beyond its range of motion, it will cause the CO2 cartridge to inflate the airbag because you are leaving the bike, and therefore it will inflate the airbag and provide more cushioning for an accident. The other approach that's coming in is kind of more of this AI-driven approach where there's a computer on board with an IMU. It's recognizing all of the inertial movement that is happening to you as the rider. And based upon some intelligence that it's seen from other models, it can then notice that a particular movement is likely to indicate a crash and therefore will inflate the airbag. Well, if we think of some of this other AI software that I mentioned, well, these sensors now could be involved to get you ready for an accident even earlier because it could recognize, for example, the radar is seeing that a collision is imminent. So even before you've departed the bike, it may be able to indicate and say, hey, get ready for this. This is a likely occurrence. So the more intelligence, the more sensors that we have, the more likely we can avoid some of these incidents. You may also start to see more airbags physically deployed on motorcycles. I believe the Honda Goldwing actually has this today where there's an airbag physically on the bike so that you don't have to have one on the rider only. And we may start to see this deployed into more of the other type of touring style motorcycles. We've covered a lot over the first 100 years of motorcycles, really focusing on the mechanical improvements like telescopic forks, fuel injection, disc brakes. But the rapid innovation of the past 25 years has been mostly in the electronics realm. And systems like ABS, traction control, adaptive cruise control, quick shifters, and even fully automatic shifting have already arrived. TFT dashboards offer even more connectivity and varied displays as you need them, offering navigation on the dashboard either through a proprietary system like that on the BMW F900 GS, or using something a little bit more generalized like CarPlay or Android Auto. And finally, I looked at the future and what may come from powertrains, as well as some assistive and safety systems. So my question for you is, what is the one piece of technology on your motorcycle that you can't live without? Share your thoughts through the text to show link in the show notes, or leave a voicemail at throttleandroast.com/voicemail. Thanks for listening. I'll talk to you next week. Hey, if you enjoyed this episode, please tell a friend about the show. You can often share an episode directly from your podcast app, or you can direct them to throttleandroast.com. Word of mouth is the best way for us to grow and find new listeners, so I really appreciate your help.